In July 2026, a compact polynomial formula appeared on X with an enormous claim. The Jacobian conjecture was false. The problem had survived since 1939. It asked whether a polynomial transformation that is perfectly reversible in every tiny neighborhood must also have one global polynomial undo button. For decades, the local evidence looked almost impossibly strong. Yet this new map keeps every infinitesimal piece uncrushed, while sending 3 different points to exactly the same destination. If that calculation is correct, no inverse can exist. To see why this was so surprising, and why the final check is much easier than the discovery, we need to build the idea from one ordinary derivative. Start in one real dimension. A derivative measures how a function stretches a tiny interval. If the derivative never vanishes and keeps one sign, the graph never turns around, so 2 inputs cannot collide. Over the complex numbers, the polynomial version is even stricter. If a one-variable polynomial has a derivative with no complex root, that derivative must be constant, so the original polynomial is linear and obviously invertible. In several dimensions, one derivative becomes a whole matrix, the Jacobian matrix. Each column records how the output moves when one input coordinate changes. Its determinant measures the signed volume scale of a tiny box. A non-zero determinant means the tiny box remains a genuine box rather than being flattened. The inverse function theorem now gives a powerful promise. Wherever the Jacobian determinant is non-zero, the map has a smooth inverse nearby. Zoom in far enough, and everything looks reversible. Keller asked whether a polynomial map from complex n-space to itself, whose Jacobian determinant is one fixed non-zero constant, must have a polynomial inverse everywhere. This is the Jacobian conjecture. The dangerous word is everywhere. Local invertibility forbids folds and collisions close to any chosen point, but does not immediately control what distant regions do, especially through complex infinity. Think of 2 explorers using perfect local maps. Every neighborhood is accurate, yet paths arriving from very far away might still reach the same place. The missing ingredient was global control. Keller proposed the conjecture in 1939. Progress came mostly by reducing its apparent complexity. Work by Yagzov and by Bass, Connell, and Wright showed that it was enough to understand special maps of degree 3 after adding extra variables. Druzkowski reduced the shape further to a highly structured cubic form. These were major advances, but they also revealed the trap. Low degree does not mean low global complexity, and adding dimensions can hide behavior at infinity. Enormous families and many special cases were checked. Dimension 1 was easy. The 2-dimensional complex case remained open. Higher dimensions were believed by many to behave similarly, but no proof survived and no explicit collision was known. The conjecture looked simple enough to state in a sentence and difficult enough to absorb decades. To defeat the conjecture, one map must pass 2 tests that appear to fight each other. First, its Jacobian determinant must be the same non-zero constant at every point, guaranteeing local reversibility everywhere. Second, it must fail globally. The cleanest failure is a collision, distinct inputs with the same output. The announced construction works in 3 complex variables. Write the output as P, Q, and R. Introduce A equal to 1 plus xy, and B equal to a squared times z, plus y squared times 4 plus 3xy. Then set P equal to AB, Q equal to y plus 3xb, and R equal to 2x minus 3x squared y minus x cubed z. It looks engineered because it is. Expanding the full 3x3 determinant directly works, but it hides the mechanism. On the region where A is not 0, introduce a projective-looking coordinate S equal to x divided by A. In the coordinates P, Y, and S, the complicated map becomes unexpectedly small. Q equals y plus 3ps. NR equals 2s minus ys squared minus ps cubed. Now split the transformation into 2 stages. From x, y, z to p, ys, the Jacobian determinant is negative a. From p, ys to p, q, r, the determinant is 2 divided by a. Multiply them. Negative a times 2 over a is exactly negative 2. Because the original determinant is a polynomial identity, equality on the dense region, a not equal to 0 forces equality everywhere, including equal to 0. So the local test is passed. The determinant is always negative 2. Now comes the global failure, and it is almost shockingly concrete. Evaluate the map at 0, 0, negative 1/4. The result is negative 1/4, 0, 0. Evaluate it again at 1, negative 3 halves, 13 halves. The result is the same. Finally, use negative 1, positive 3 halves, 13 halves. Again, the result is negative 1/4, 0, 0. 3 distinct points occupy one fiber. Any inverse would have to take their shared output back to 3 different inputs, which a function cannot do. The conjecture is therefore false in dimension 3. Adding untouched coordinates gives counterexamples in every dimension above 3. This construction does not settle dimension 2, which remains open. According to Levent-Alpog's announcement, Uncle Matthew suggested investigating the problem, and the AI model fable produced the work leading to the counterexample. The full discovery path has not been published in enough detail to reconstruct every creative step, so it is safest to separate provenance for verification. The formula itself can be checked by symbolic algebra in seconds. Differentiate, compute the determinant, and substitute the 3 points. Independent mathematicians also encoded a normalized version in Lean, where the determinant and collision become machine check statements derived from explicit definitions. This is a perfect example of an asymmetric mathematical problem. Finding the object may require a vast search or a clever reparameterization, while checking it is short and decisive. AI did not replace proof. It proposed an object that humans, computer algebra, and a proof assistant could audit from different directions. The surviving picture is now sharply divided. In one variable, the statement is true. In 2 variables over the complex numbers, it is still open. From 3 variables onward, this explicit collision makes it false. The deeper lesson is the local global gap. A constant Jacobian controls every infinitesimal neighborhood, but without properness, points can escape through infinity and global branches can meet. A corrected theorem does survive. A proper polynomial map with non-zero constant Jacobian is a polynomial automorphism. And the research lesson is just as important. New AI systems can search unusual algebraic instructions at a scale that changes which risky problems are worth trying. But public formulas, independent derivations, formal verification, and human understanding remain the bridge from an astonishing claim to mathematics.